It looks like we're about ready to get started, so thank you all for coming in and for hanging out all the way through the end of the day. I appreciate it. My name's Wade Schulz, and I'm a physician scientist in the Department of Laboratory Medicine at Yale University and the Yale University School of Medicine. And in addition, I also manage a large portion of our data science and Hadoop cluster for our health system at Yale New Haven Hospital. And today I'm going to be talking about enabling digital diagnostics with a data science platform. And what I'm going to really try to do is keep a high level and try to walk through how we went through creating our data science platform, how we picked our tools to do that, and walk through one of our clinical use cases with a machine learning project. So just to look at that as, again, a quick summary, the main thing that I really want to try to focus on is trying to select questions that can really emphasize how your data science platform works and show its goal and its real potential and how you can have impact and outcomes very early on for those who might be stakeholders in investing in that platform from a managerial perspective. So one thing that's really unique in healthcare is that traditionally we really haven't had much for big data sources. Within Yale New Haven Health, our hospital's the fourth largest in the United States in terms of beds. Our entire electronic health record, not counting imaging, only comprises about 5 terabytes of data. So the real clinical data really isn't that big of a data source. However, as we move into our clinical imaging, laboratory testing, and other data sources, such as new sources like genomics, we really start to move into actually getting some of that big data in healthcare that many of you are probably already familiar with. And some of the use cases that we've started to work on at Yale include real-time patient monitoring. So every patient in every one of our ICUs and all of our monitored floors, we get all of their vitals between every 1 and 5 seconds from EKG machines, pulse oxes, ventilators, and all other attached devices. We're also starting to integrate wearable data through our patient portals, through HealthKit, and through other sources so that we can pull in those home monitoring signals into the electronic health record. And then also working on several large projects related to genomics, and not only the basic biomedical science, but also how can we take those and really start to make clinical insights at the bedside so that we can get impact and decisions made within a couple of days of testing for patients. And the push for big data sources and big data analytics in healthcare has really gotten a big push over the last several years. Within the United States, the National Institute for Health just started our Precision Medicine Initiative with a goal of enrolling 1 million patients, as well as the Cancer Moonshot, both of which are very large investments for healthcare data research and really focused on the big data and data analytics. And to try to take advantage of these funding sources and try to really make some impact on some of those other data sources, we started to build a data science platform within our health system. And these are a few of the core technologies that we're really using out of Hortonworks. Scoop, Storm, and HDF for our data ingest and streaming data, HDFS and Elastic for some of our data management, and then Python, Spark, and Docker for more of our application-based programming. And like I said, I'll walk through all of these and how we've chosen these through a use case over the next several slides. One other aspect that I wanted to point out is that because we are in healthcare, we have had to secure and Kerberize our entire cluster, which is definitely a bit of an undertaking. If anybody has questions about that later, I'd be happy to discuss, but is something that can be done and does integrate nicely with all of these tools now. So working through our data science journey, what's very common, and this is even true of those funding opportunities that I just showed you with the Precision Medicine Initiative and Cancer Moonshot. With big data, we often say, let's get the data, stick it somewhere. We'll do something with it, and later on that's going to do magical things. However, defining that question is often difficult, done later, and because of that, it's sometimes tough to really explain to our stakeholders, why are we investing so much money into this hardware, this technology, training, and HR resources, when we don't really know what we're going to be doing with the data once we capture it. And one thing that I'd really try to, oops, I skipped over one there. Okay, so one thing I'd really try to emphasize is, as you're going through this data science journey, is try to form some of your data science questions. Try to focus on things that you can do quickly and get some output from early on, and then set some long-term goals as well. For the scientific community, we're very focused on hypothesis-driven research, so how can we make a question and then later on try to answer that and prove it true or untrue. The next step that ends up taking a lot of time is always assessing our data and cleaning it up as necessarily, and then finally getting to the fun parts, which are writing the code, doing the testing, and getting some output from the data that you got initially. As you look at different types of analytics you can do, the 4 general types of analytics range from descriptive to prescriptive. And really, when we're trying to define stuff for our data science clusters, we really try to stay to these predictive and prescriptive types of analytics. The descriptive and diagnostic are helpful, so defining what's in the data set, how many patients might have been intubated, how many had successful intubation. Diagnostic, do we have an impact by making a treatment change? But moving into really more, how can we provide treatment recommendations or better outcomes by using these analytics, something that we can't do with our existing data and our existing analytic tools. So to try to define this a little bit more cohesively within an actual use case, I'm going to walk through something that we do in our clinical laboratory. So at Yale New Haven, we have a central clinical laboratory as well as a reference laboratory. It's this building in the back. We do about 10 million laboratory tests per year, including genomic testing, and that results in about 46 million test results annually. One thing that really leads to large turnaround times, as we call them, so something that takes a significant amount of time from the time of test to the time of output, is that a large number of our tests require clinician or physician interpretation. So genomics, flow cytometry, most of our cancer diagnostics, after it's been run on one of our laboratory instruments, we actually have to have a physician look at that output under a microscope or on a spreadsheet or within a PDF and actually try to interpret what those results mean. And because of that length of time, it really takes a lot of time. The one that I'll work through here is a blood smear. From the time of order, it's often about 48 hours until we actually have an interpretation, which can really delay treatment in some instances. So going back to, can we define our problem and really try to implement something with our pipeline that can have an immediate impact? Our clinical question here is, can we use our big data and machine learning to improve our diagnostic reproducibility, as well as increase our throughput through the clinical laboratory? And our hypothesis was that by doing this, we would be able to improve both of those things, and in addition, be able to provide an actual quantitative or numeric result for tests that are often qualitative or just descriptive. And the test that we chose to look at first was a peripheral blood smear. So this testing, basically what happens is we take a tube of blood. This doesn't happen on every patient, but we do around 500 of these per day. After being run on our automated analyzer, it creates a peripheral smear. So it takes some of that blood and slides it on a glass slide. We then have to set it in a microscope and look at an image like this under the microscope. And we look a little bit closer, but we have to try to pick out all of these different cell types. There's actually about 20 different types total. And from that, we tried to make a report that says, are there a lot of elliptocytes or some schistocytes or an increase in dacrocytes? And these changes actually have clinical impact in many types of patients, things from iron deficiency to lead poisoning to very rare diseases like TTP. So there's a lot of different differences in range and clinical impact. From looking at the smear right now, what the clinical interpretation actually comes out to be is a text block like this. So after I look at this on the microscope, this is what I would basically put into the patient's chart. There's frequent dacrocytes, some occasional target cells, and this might be due to iron deficiency anemia. And then we would recommend further testing. What our goal with the machine learning is to take this qualitative and very basic explanation and actually run that through a computer much faster and actually get a numeric result. So by comparing this to normals, we could say that there is definitively an increase in dacrocytes and target cells. And because of this pattern, along with our other integrated labs, this patient does have iron deficiency anemia. So really increasing our turnaround time, making a more definitive diagnosis, and getting faster care for our patients. So from the computational side, the question is then, how do we get from our current workflow and actually get that into something that's computational? So how do we go from specimen to output and try to automate that as much as possible while not taking too much time to actually put that into a workflow? And if we break this up into our basic steps from the computational side, we have our data ingestion, storage, analysis, and then how we coordinate that. And before we actually started developing our workflow, we went through and tried to choose the best tools that would actually fit for our data sources. And I'll walk through each of those here. And feel free to take as many pictures as you want. I'll also stick this on my website, which I'll have at the end. So if anybody wants it there, you can all get the high quality ones later. So for data acquisition, we really went through a technology assessment looking at all of the different tools. And we were familiar with all of these from some different use cases that we were using. But we were really trying to focus between Storm, Flume, and HDF for acquiring these images from that automated instrument. So that automated instrument just takes a bunch of JPEGs of the slide as it comes out, and we needed to move them from that hardware into our cluster. From some of our prior work, Storm we had used a lot for our real-time patient monitoring. It has great capacity and scalability. It was able to keep up on some of our workflows where some of the other tools didn't do quite as well. The downsides for this are that you definitely need a developer to get these pipelines up and deployed out. It's also a little bit difficult to debug and test in production. One thing we typically run into with a lot of our laboratory instruments is that our vendors are not always very forthcoming in terms of APIs and interfaces, because it's often in their best interest to keep those locked down so that we can't actually access them. So trying to do something where you don't have great production debugging is definitely difficult in the clinical setting. Flume, good capacity and easy to scale. Some of our issues there is that for doing the type of interaction we needed to, again with the instruments, would require a lot of custom development and was a little difficult to implement. So what we finally ended up going with was Hortonworks Dataflow or NiFi, which we had also used in streaming in some of our laboratory data. HDF has good capacity. You can definitely scale to Storm size if you want to by deploying to enough nodes. The nice thing is that it's very easy to debug with our data processors. We can also use some of the built-in data processors or develop custom ones as necessary. And for this workflow, we were actually able to use all of the native, we didn't have to do any custom dev. We were able to use all of the native processors to pull the files off the instrument and get those into our storage pipeline. From the storage perspective, I won't go into any real deep detail, but basically we're using a combination of HDFS for permanent storage and to store all the images, and then Elasticsearch to store all of our metadata and results. From the analytics perspective, we were looking really at two different approaches, either using Spark or using Python. And all of our development initially, I'm not sure if anyone was here for the last talk, but our data scientists that had started this had all started with Python. But we were really interested in, could we migrate this to Spark to get into the production pipeline? Some benefits of Spark are, again, the scalability. It's relatively easy to develop in, and it has really good integration with the other tools within the Hadoop platform. So grabbing data from HDFS, getting stuff back to, whether it be HDFS or Elasticsearch or another tool, was very nice. Some of the downsides, definitely less mature machine learning frameworks, and the GPU support, while that's coming along, was a little limited at the time. So for our image analysis, processing here was actually a little bit difficult. So we ended up sticking on the Python side for all of our analytics. Some of the downside here is that scaling, you have to do a lot more of that scaling manually, but can definitely be done. But the payoff for using some of our GPU-enabled machines was one of the big reasons we went the Python route in the end. And one other note is that all of our Python scripts do get Dockerized within our cluster, which does make it easy to deploy and scale those as necessary. So this was our overall tech stack that we settled on at the end of the day. So we come off of our automated instrument, go into our Hortonworks Dataflow, and put that data into HDFS. That then triggers the analysis with Python scripts within our Docker containers. Those results go to Elastic, and all of our downstream analytics comes off of Apache Spark. So this was very quick and easy to get out, relatively speaking. Overall, we've been working on this on and off for probably about 6 to 9 months now, but with only 2 people very part-time. They have other projects they work on. So while it's a big undertaking and machine learning often looks very scary, definitely something that's achievable even with small teams and even in a clinical setting. So just to dive into a little bit more of what we're doing on the machine learning side, I'll try not to get too technical, but just some more details in case anyone is interested. What we ended up going with is a convolutional neural network, and these are I don't want to say newer, but being adopted more recently, especially for image analysis. And the idea is that, as with all machine learning, your image goes in, things and magic happen, and out comes your interpretation of what actually was your image in the first place. The idea with convolution is that the opposite of deconvolution, you kind of take your image, and if anybody does a lot of convolution, ignore my very bad technical explanation here, but you basically fuzz areas of the image so that you're not looking at very discrete areas, but you take a region of the image and feed those regions into your neural network, which can have better output, especially things that are fuzzy, grainy, or may not be the best input images to start with. And by using this approach, we actually got fairly good precision and accuracy very early on with our pipeline. So by using around 80% of our training set, we were able to get up to about 99% precision. There are a few cell types that we were a little light on for our initial training set. And so some of those, I believe it was dacrycytes, has our highest percentage of off, but something that, again, with very little effort, you can get pretty good percentages. To get really good, definitely requires more effort and more training. So from the machine learning perspective, one question I get asked a lot when I do these talks is, how many PhDs or do you have applied math? Who's working on the actual machine learning part? Because often these are fairly difficult pipelines, and I will admit we do have one applied physicist who does most of the machine learning part for us. But from the initial starting point of if you want to get started on a machine learning project and actually just try to prove the value or that it might be worth it, it's actually not that difficult to do. A lot of the problem is actually more on the labeling and data preparation side, really, than any of the machine learning. So getting these images off of the instrument, getting individual red cells cut out of the overall, larger imaging, and all of those more basic programming steps have taken much more time investment from us than the actual machine learning pipeline. And when you look at our first set of code for the machine learning development, in less than 15 lines of code, this is using Keras and Theano. I think it's like 13 lines of code was the first pipeline we put in that came out with about 65% accuracy. So again, to get to something that's better and has much more predictive value is going to take a lot more fine tuning. But to get started is really not that difficult. And there are a number of tutorials online that give you very similar code to get started with any of these projects. And this one says conclusions. I know I've got a little bit or quite a bit of time. I'm actually going to skip down to some other use cases that I have in the presentation and come back to the questions later on. But to summarize this part, machine learning really can do things, and even in a clinical setting and with fairly little input from users and developers. One nice thing with the Hadoop platform, and even with Kerberized and secured environments, is that other frameworks and other tools can be integrated fairly easily. So whether that be custom Python scripts, Elasticsearch, or anything else, just because you've chosen one technology stack, even integrating those other sources can be done, especially if there's a strong use case need for it. For people looking at bringing on new ingest, I would definitely recommend taking a look at NiFi. We use Storm quite heavily in many of our projects, but we've been transitioning a lot of our smaller volume workflows to NiFi just because of the ease of development and implementation. And one other comment is that, while a lot of these big data workflows do seem complex, you need to link together all of these different steps, they are very reproducible and have reusable architectures, which you'll see in some of the next slides that I'm going to show to you here. So some of the other healthcare use cases that we've had that take similar workflow approaches, one of them is our patient monitoring workflows. So this is one that I had mentioned early on, where all of our patients that are connected to monitors, EKGs, telemetry, ventilators, send all of their data to these central servers between every 1 and 5 seconds, and we generate about 6 billion data points per month off of these systems. We consume these from raw, what's called HL7 feeds, which is a healthcare data standard. Feed those in through a custom service for some security and data management reasons that we had to address. We go into Kafka, Storm for our processing and initial analysis, and then into HDFS for storage with all of our analysis with Spark. And just as an idea of how fairly easily scalable this is, we were initially running this on a 20-node cluster, and 1 year of our data we could process for doing some basic operations within 10 minutes, and that was at collecting 6 billion data points a month. So very scalable and very performant when you've got these architectures in place appropriately. One of the other things that we do a lot of is looking at our laboratory data, and this is for doing something that's actually fairly basic, which is business intelligence. So we can do more advanced analytics on our lab data, but one common question is, what is our turnaround time? So, for a marker of myocardial infarction or heart attack in the ER, how fast can we get that result back out to the doctor? Because we actually have contracted times with our ERs that we promise we will get this to you in 10 minutes or 30 minutes or 60 minutes. So how do we make sure that we're achieving that? And this is the workflow we use to do all of those analytics. So again, we come off of our messaging interface into an emissary service, into Kafka. For this, we use NiFi for all of our data processing, and then ship those messages into HDFS for permanent storage, and then Elasticsearch for all of our real-time analysis. And then we use Kibana for our visualizations. And this is just an example of one of the visualizations that we use with the Kibana tool. And from this, we get our total laboratory orders, our total lab tests that are outstanding. We can see our test volume, turnaround time, and the nice thing about Kibana is that all of these are interactive. So if you pick a test or a laboratory location, all of the rest of the plots update in real time for you. So you can see what is our turnaround time for troponin from our main lab or from one of our reference laboratories, so that we can get all of that data and have it within milliseconds of the test being ordered or the result being sent out. And then a few of the other things that I just wanted to touch on briefly. One of them is the Precision Medicine Consortium that we've actually been working on with Hortonworks. And the goal here is that we've been trying to look at what could we build as a genomics platform built on the Hadoop ecosystem. So we've been really pushing for more precision medicine and more genomic testing within our healthcare system. One thing that we often run into is that genomics is not it's very well regulated, but there are very few commercial tools out there to help with that management. So our requirements for data storage, security, and governance really aren't commercially available. So we've been looking at how could we build that on Hadoop and open source tools to really get that available for academic and clinical centers across the world. And we've already started some of this work. We've done some papers and publications and posters on this, just looking at how can we get variants into these systems with the goal of moving all of our genomics there in the future. And for anyone who might end up being in San Jose at the summit there, we'll be talking about this a little bit in more detail, but we've also been working on a 5 million person trial in China with collaborators at the National Center for Cardiovascular Disease. We've got 1.6 million people enrolled already with 400,000 biospecimens, with the goal of sequencing, whole genome sequencing 30,000 of those individuals by the end of this year. And we're using Hadoop for all of our data management for that platform. So after they do their surveys, collect their biospecimens, all of their data comes into Hadoop, and we do a lot of our downstream analytics within that platform, and it's been very nice for being able to, again, scale easily. We've got several GPU-enabled machines on there so that we can do machine learning based off of their EKGs, angiograms, cardiac imaging, and we're growing this very quickly. We started off with just 5 machines as a demo. We're up to about 40 machines with a couple of GPU-enabled boxes now, and are continuing to scale that as we move more into genomics. So that's basically all I've got for the presentation. I'd be happy to take any questions, and then we can get to more important parts of the conference after and get you out a few minutes early. So thank you for your attention. Yeah, so the question was whether we're moving into being able to interpret things like radiographs, and absolutely. So one of our first projects that we're looking at is actually something in our neonatal intensive care unit for something that's not extremely common, but we test quite a bit. That's basically an abdominal infection in neonates. And a lot of them get abdominal x-rays, and the diagnosis can often be missed by radiologists, but you can typically pick it up after once you know it's there. So we're actually hoping to start that within the next couple of weeks, where we'll actually be pulling in all of those radiographs and doing a very similar approach to doing diagnostics with more standard medical imaging.
Let me start with a remark, and then I've got 2 questions. First remark is, I think this is the best presentation that I've seen today here, because you did talk about the step 2. And that explains the result that you showed then afterwards, because most presentations keep still the step 2 in the dark, and you don't know how they came to the result in the step 3. So that's the difference for this presentation. Still 2 questions about the step 2. You did say you used Python for the analytics. Did you use that on the Hadoop cluster nodes or on separate hardware? Because you use there the GPU types, right?
Yep.
And then the final question is, I mean, which product or library did you use for the machine learning algorithms?
Yeah, so for the first question, basically we have some nodes that are integrated. We actually call it our data science cluster, because some of them are Hadoop, others are not Hadoop, but we have fairly tightly integrated with our Hadoop platform. So we've got now 32 nodes that run the core Hadoop services, 3 master nodes, some edge nodes, and data nodes. We also have a couple of nodes that are separate from that have GPUs on them that we have Spark installed on. We do most of our Python scripts there, and then we've got all of the Hadoop clients, but we don't really have any of the other Hadoop services on. So they can access Hadoop resources, they can run Spark jobs, but we don't do any of the actual data storage there. We also have 7 nodes that are Elasticsearch oriented for doing our Elastic cluster. So overall, we've got several different things that we can ship to, and we've actually just been talking with some of the engineers recently about how can we better manage some of that using yarn labels and stuff along those lines. So they're integrated, but not always on the core Hadoop machines. And what was the second question again? Oh, the libraries. Yeah, so the libraries, we've tested a lot of them. So the one person who actually does a lot of our machine learning development is actually one of the core contributors for Lasagna, so he uses that a lot. We use Caffe, we use Theano, we use TensorFlow. For the one that I showed you, we're actually using Theano for the red blood cell images. But we use kind of a wide variety for really no particular reason right now, other than we kind of jump around a little bit. We've been meaning to actually kind of go through and do a more formal review of why do we sometimes select one over the other. So if anybody else has recommendations, let me know. But we've never really gone into a real in-depth, is this library the best, other than which one's easy to get up running and is usable from the programming standpoint. Yeah.
You said that, maybe you mentioned it, but you said that the original blood tests were taken at 48 hours until you had a diagnosis, which was more or less complete. How long does it take now?
So right now we're still going through the clinical validation. So the problem in medicine that we still have is black box. Doctors don't like black boxes. So we're going through our clinical validation to basically show that we have very good continuity between physician interp and the machine learning interp. The actual image analysis is done within 10 seconds. So from the time that we have the image, our algorithm can have output within about 10 seconds. So in theory, that would be your minimum turnaround time. Likely, we'll still have some physician oversight and sign off on that, but the idea would be that we could do that much more routinely and rapidly by using those numbers, or maybe pushing forward the number but not the final diagnosis until after a physician has seen it. So we're still working through that, but our goal is that we can get at least some of our stat images. So one of them that we often run into is a disease called thrombocytopenic purpura, TTP, because the other one's too hard to say. And it's basically due to an antibody that ends up causing issues on platelets. And because of those issues, you end up with schistocytes, so those red cells end up looking chewed up. And our current diagnosis for that is, so it's this third cell here is a schistocyte. And in a typical image, you don't really have any, but in a person who has TTP, those will be increased. And that is basically one of the diagnostic criteria right now, schistocytes increased. We do that by looking at a number of high-powered fields, but it's not done very well. But the idea would be that even if it's at 48 hours, being to provide an actual percentage of how many of these are there provides a much better diagnosis than the human looking at it and saying, hi. Great. Well, if there's any other, oh, right here.
How many machines are involved in this turnaround time statistics?
For the business intelligence, or for this one?
For turnaround time of delivery of results in laboratory.
So for actually doing the result, or for calculating them?
Calculating and providing this turnaround.
Oh, gotcha. So for calculating it, basically for doing that laboratory BI use case, it's on our shared cluster, so we're using kind of all of the nodes to some extent. NiFi, we're actually only running on one node right now, so we've got one node that does all the processing for this. Our upstream stuff coming from Cloverleaf and all of our actual instruments, there's a ton of machines. Here we run a 7-node Elasticsearch cluster, but it's shared between several different, it's got a lot of data sets in it. So overall, this, we don't generate all that much data. So you technically, if you wanted to, you could probably do this on a single server that was moderately spec'd. If you want failover production, everything else, then triple all of that. Yeah.
So I have two questions. The first one is, how long is it taking to you to make a whole genome sequencing in hours or days? And the second one is, of course, you are doing a lot of work with GPUs. What about FPGAs, so field programmable arrays? Are you doing some kind of work, or?
So the second one I'll do first because it's easier. We haven't started anything there yet. Probably.
I understand that, for example, for genome sequencing, it is quite, you can have some it's very difficult, of course, to get them to work, but you can have some increase in performance really important.
Yeah, absolutely. And the genome sequencing is a tricky one, so there's a lot of caveats in terms of how long does it take to do. So from a broad estimation, I would say that, within part of a day we could sequence a whole genome. Within a couple of days, depending on the hardware, maybe less, 1 day to a couple of days. We can do the computational parts of aligning that and doing the variant calls. If we want to get into more detailed analysis, then it's going to be a couple of more days. So, the overall kind of general guideline is, for between $1,000 and $5,000 and between 2 and 5 days, we can get a whole genome done. And then all of the other details fall in. So there's sequencing depth. Are you looking at tumor? Are you looking at normal human cells? Are you looking at both? Are you looking at point mutations or larger rearrangements in the genome? So a lot of variation, but 2 to 5 days and $1,000 to $5,000. Great. Well, if there's any other questions, I'll stick around for a few minutes. Otherwise, enjoy the rest of the summit, and I'll hopefully see some of you in San Jose as well.